Hi, I'm Alex Swan. In this video, I'll be solving a problem involving a protein-ligand complex and binding equilibrium and the dissociation constant of the interaction, Kd. It's important to understand that even though protein-ligand interactions simply involve the binding of a protein to its ligand, the reaction is nevertheless a reaction in chemical equilibrium. In the example I'll be discussing, the protein's ligand is DNA. However, keep in mind that the dissociation constant is applicable to any protein-ligand interaction, such as a protein-RNA complex or an enzyme-substrate complex. For a protein-ligand interaction, the dissociation constant, or Kd, measures the strength of the interaction and is given by this expression, where P refers to the equilibrium protein molar concentration, D refers to the equilibrium DNA molar concentration, and Pd refers to the equilibrium molar concentration of the DNA protein complex. It's important to remember that the concentrations specified in the Kd equation refer to equilibrium concentrations. For this reason, I usually like to specify Kd like this, where it's clear that the concentrations must be those at chemical equilibrium. You'll notice that the Kd is simply the reciprocal of the equilibrium constant, Keq, which you encountered in general chemistry. In fact, all Kd problems can be solved using the same methods you used to solve problems in general chemistry, at least problems dealing with chemical equilibrium. In this video, I'll show you how to do just that. I'll be solving study question 5.3. The question reads, the Kd of a typical DNA binding protein is 10 to the negative 10 molar. The volume of a typical bacterial cell is 1.5 times 10 to the negative 15 liters. A bacterial cell contains 1 molecule of DNA. If the cell contains 10 molecules of the DNA binding protein, in what proportion of cells at one instant in time will the DNA be bound by protein? First, I'll write out the reaction and set up an ice chart, which you encountered in general chemistry. The first row refers to the initial molar concentrations of the products and reactants, and the last row refers to their equilibrium molar concentrations. The middle row refers to their change in molar concentrations, that is, the difference between the initial and equilibrium molarities. The first step is to fill out the first row, that is, to find the initial molarities of the products and reactants. Remember that molarities are calculated in moles over volume, which is given in liters. Thus, if I want to express the initial molarity of protein, I need to first convert 10 molecules of protein into moles of protein, and then divide that result by the volume it can occupy, that is, the volume of a bacterial cell, which is given in the problem. I use Avogadro's number to convert to moles, and I calculate the initial protein concentration. I then substitute this back into my ice chart. I can find the initial concentration of DNA in a similar way. Recall that a bacterial cell contains only one circular chromosome. Thus, each cell contains one DNA molecule, which I convert to moles and divide by the volume. This number also goes into the ice chart. The last thing I need to find is the initial concentration of the protein-DNA complex, which is simply 0, because no complex is formed if a reaction hasn't yet taken place. Next, I need to determine expressions for the equilibrium molar concentrations of the products and reactants. Since I'm not explicitly given this information, I'll need to define a variable. I'll call x my change in protein concentration. How do I find the change in DNA concentration from that? Recall that the protein and DNA react with one another in a 1-to-1 mole-to-mole ratio and produce 1 mole of product. That is, if the protein concentration drops by an amount x, the DNA concentration must also decrease by that same amount. Another way to see this is that I can multiply x by the mole-to-mole ratio of DNA to protein, which is 1 over 1, and my units cancel out, leaving me with x. I can do the same thing for the change in Pd concentration, and this is what I get. I can then express my equilibrium concentrations as such. The next step is to substitute these equilibrium expressions into the KD equation as such. The problem specifies the value of KD, which is 10 to the negative 10. Now all I need to do is solve this equation for x. First I multiply both sides by x to get rid of the fraction, then I set the expression equal to 0, and then I find the roots of that equation using the quadratic formula. Doing this, I find that x is equal to 1.096 times 10 to the negative 9. Now that I have x, I can go back into my ice chart and substitute x with what I found. My ice chart is now complete. A filled-out ice chart contains everything you need to solve a KD problem. In this case, we're asked to find the population of cells at one instant in time in which the DNA is bound by protein. This is the same thing as asking for the ratio of the equilibrium concentration of the protein-DNA complex to the initial DNA concentration. Substituting my values for my ice chart, I obtain 0.99, meaning that in a given population of bacterial cells, 99% of them will have a protein bound to their DNA.